In our last few lessons, we found some relationships between the graph of f and f prime. In fact, we made a very similar table to what you see in front of you. So it didn't have this last column and it had an extra row. But the idea is, if you know what f is doing, you know what its derivative is doing, and vice versa. If you know what f prime is doing, you know what f is doing. What I did today is, instead of f and f prime, I just changed the names of the functions to s and v, because we know v is the first derivative. So this is essentially like our f of x column. All right, so here are some statements we made yesterday. When a function is increasing, we said its derivative is positive or above the x-axis. We'll come back to this column later. So again, when a function is increasing, its derivative is positive. When position is increasing, its derivative, velocity, is positive. And we're going to say the exact opposite, right? When a function is decreasing, its slope or its derivative is negative or below the x-axis. And the same then is true between s and v. When the position is decreasing, the velocity is negative. The other one we looked at was that smooth max, min, or shelf. And when a function has a smooth max, min, or shelf, its derivative is 0 or on the x-axis. So what I would like to do is tie this into what we already know about the motion of a particle, right? If the position is increasing, well, think about the particle on an axis. If its position is 1, then 2, then 3, then 7, then 12, then 15, the particle is moving to the right. If it's on a vertical axis, it would be moving up. We've already said this. If the velocity is positive, we're moving in the positive direction. Velocity, remember, is speed and a direction. So when the velocity is positive, we're moving to the right or up. Which means when the velocity is negative, we are going the other way. We are moving left or down. Now, when the velocity is 0, or when the position, we are at a max, min, or shelf, we would say the particle is at rest, right? It's not moving. Its speed is 0. I'm going to leave a little note here and say it is possibly changing direction. That's something we'll come back to today, I think. So again, these two columns are a repeat from yesterday. I'm just using different names for the functions. And this is just really relating these pieces of information to what our particle is doing. It's very descriptive. Okay. All right, so these next 3 slides are all related to this graph right here. It says a particle moves along a horizontal axis. It's moving side to side, left and right. Its position over time is shown in this graph. So they're giving us the position function, which is the equivalent of giving us the original f of x. All right, first question says, when is the particle moving to the right? All right, well, let's see. I've got a position function. The particle is moving to the right when the position function is increasing. This is really not new. We looked at this a little bit before. So when this graph is increasing, I would say that happens from 2 to 6. That's telling me my particle is moving to the right. I'm just going to jot down the why, like what made us pick these times. I know they didn't say why, but why not? Which means the particle is moving to the left when the position is decreasing, right? The exact opposite. So I'm going to go up to my graph, and I don't want to make too much of a mess, so I'll just kind of highlight lightly. I can't tell that. In that green color, my graph is decreasing. I'm going to leave myself a lot of room because there's 2 intervals, from 0 to 2, and then again from 6 to 10. Then it says, I know we're going to be bouncing back and forth here, when is the particle at rest? At rest means the position graph has a smooth max, min, or shelf. So here's a min, here's a max, and I think that's it. I think those are the only two places that look like a horizontal tangent line. I mean, I think some of us could argue about time 10, but I don't think it looks completely horizontal there. So I'm going to say t equals 2 and t equals 6. Honestly, I should have done a better job of saying on the open interval 0 to 10, which means don't look at the endpoints. Okay. All right, here's an old question for us. It says find the particle's displacement on the time interval 0 to 10. Displacement, remember, is the change in position. The position at 10 minus the position at 0, which we have. The position at time 10 is -4. The position at time 0 is 2. Oops, sorry, I'm losing my place. So my displacement is -6. And I put that review question in there on purpose, mostly because we're going to introduce something a little bit new. I want us to find the total distance. I'm not saying the concept is new. I'm just saying we, as a group, have not looked at this yet. So displacement is just your ending position minus your starting position, and it doesn't care what you do in between. Total distance is now more literal, like how far did the particle actually travel? So we're going to look at the graph to determine what's going on here. There's no formula for this. Like I said, we're going to look at the graph and kind of count some blocks here. At the beginning of time, we're at a position of 2. I'm just going to write this down. At time 0, my position is 2. And I travel to the left, right? And at time 2, I'm at a position of 0. So how far did I just travel? I just traveled 2 units. Then I turn around and I start going to the right. So I'm moving to the right until I get to a time of 6, and there I'm at a position of 3. So from 2 to 0, I took 2 steps. Then to go from 0 to 3, that's a distance of 3. And then I traveled to the left until time 10, and at time 10, we ended a position of -4. And so the distance traveled on that last little leg of my trip there was 7. Right? So I'm looking almost like mini displacements, or how far did I travel to the left, then how far did I travel back to the right. And so we don't need a T-chart to do this. I could have just said, oh, to go from 2 to 0, that's 2 steps. To go from 0 to 3, that's 3 steps. To go from 3 down to -4, that's 7 steps. For a grand total of 12. I'm saying steps because I don't have any units here. Right, so my total distance traveled, I just looked at vertical changes in the position graph. Think about like little, finding the distance of each little leg, okay, which gave us a total of 12. All right. So the reason I ask these questions side by side is to remind us that there is a difference between total distance and displacement. Okay. Right now, all we can do is to look at the graph to find total distance. All right. Not the last question, but the last question on this slide. Find the average velocity of the particle. This is again an old question, but this is a reminder. Average velocity is our displacement over time. Right? Technically, it's S of B minus S of A all over B minus A. I think this is a lot easier to say out loud and is a lot easier on our brains. Good news, we already found the displacement. And the time is that 10 minutes, 10 seconds, I have no idea. Reduce if you want or not, that's your choice. Right? So, again, average velocity is the slope on the position graph. So I really just found the slope between the endpoints. Okay. All right. Good. So my last 2 questions. I'm going to have to keep sliding back and forth here. But it says sketch a graph of the particle's velocity. So remember, I was given the position. which was like our f of x, and I'm asked to graph its velocity, which is like our f prime. I'm going to write that down. Given f of x, sketch f prime of x. So this is what they're asking us to do. This was lesson 2.1. This was like the spaghetti day, right? Now, I said we're weaning ourselves off of spaghetti. That was the whole point of how we started class yesterday. But I like, personally, and now that I've made a mess of my graph, I like to start at those smooth maxes and mins, right? Because where my original has a smooth max, min, or shelf, my derivative will be on the x-axis. So at 2 and 6, I think we should have x-intercepts, okay? Now again, I've already said it, but I don't really want us to actually use spaghetti or think about a bunch of points. I'm going to use a few. I will start by saying, we already said this, right? The position is decreasing from 0 to 2, meaning the derivative should be below the x-axis. So I do know from 0 to 2, I want to be below the x-axis. And, whoop, again, from 6 to 10. My original is increasing from 2 to 6, so I want to be above the x-axis there. So at least that gives me a good start, right? Now, for the first time in a few days, I do have a scale on the y-axis, so I actually think we should consider a few extra points. Maybe I find the slope of the tangent at the beginning. Maybe I look at the slope at around 4, or maybe 8. Right? I'm just thinking about a few points just to get myself some benchmarks. I mean, I don't know. I think at 0, the slope looks like it's -2 or something like that. Oops. I think at 4, the slope looks like, I don't know, 1.5. And then at 8, I don't know, like -3, -4, something like that. And then, oh God, I'm sorry, I know I keep moving this paper. And then maybe at 10, you look at it and you say, well, I mean, maybe like -1/2. It's not quite 0. I think right there at 10, the slope is -1, -1/2, something like that. So the only reason I did that was just to help me understand how high or how low my graph should go. And I'm just going to draw it as smoothly as I can. Our graphs might look a little bit different, but what they should have in common, the x-intercepts and where they live above and below the x-axis. Okay? All right, so maybe I'll go ahead and just label that. This graph right here is the graph of the velocity. This is the first derivative. All right, last question about this one. It says sketch a graph of the particle's speed. Remember, speed is the absolute value of the velocity. We already have the velocity. We just need to make it positive. Make velocity graph positive. Well, it's already positive from 2 to 6, right? I just need to flip this up. So instead of starting down here at -2, I'm going to start up there at +2. I'm just doing a little reflection. This is going to flip up and this is going to flip up. So let's see, at 8 was I like down there at -4, so I'll be up there at +4. And I'm not going to say smooth it out this time because the nature of an absolute value transformation is going to create some cusps, right? So there are sharp points in the speed graph. That's okay. But once you have the velocity, you just flip any negative parts up to get your speed. All right. So let's flip it over to the back. So these last 3 slides are now about a new graph. It says a particle travels along a horizontal axis. Okay, so that's the same. The graph of its velocity is shown. So remember on the front, I gave you the graph of the position. And now I'm giving us the graph of the velocity. This is like me giving you the graph of the first derivative. In fact, time out. this is what we're looking at. This is the graph we have, okay? So my first question, I think, when is the particle moving to the left? All right, a particle's moving to the left when its position is decreasing, but I do not have the position graph, or when its velocity is below the x-axis. So again, because I have the velocity graph, I'm looking to see when the velocity is negative or when the velocity is below the x-axis. And that's going to happen from 0 to 1 or 5 to 9. Same question I asked on the front, but we're getting the information differently because we have different information, okay? All right, now, I didn't ask when the particle's moving to the right, but that just means everywhere else, okay? So part B says, when does the particle change direction? Okay. A particle is possibly changing direction, we'll talk about that, when the velocity is 0. All right, so let's go back here. My velocity is 0 at 1, 5, and 9. These are candidates. These are possible places where we're changing direction. So I'll write T, I'll come back to this list. Those are my candidates, right? But I think there are answers. Because if the graph is moving to the left when this is green, means the graph is moving to the right when it's pink. I mean, look at that, green to pink, pink to green, green to pink. Here's where I'm going to be very careful with how I write my y. I'm not just going to say that the velocity was 0. I'm going to say that the velocity crossed the x-axis, or the velocity changes sign. Saying that the velocity is equal to 0 is not good enough, because what if my graph bounced off the x-axis? Then there would not have been a change in direction, okay? So really important that we think, all right, if the velocity is equal to 0, it's going to give us candidates, but most importantly, that velocity has to change sign, okay? All right. Next question says, when is the particle moving the fastest? To me, the fastest means greatest speed. Well, remember how we were graphing the speed graph on the front? I mean, we already have the velocity. We could graph the speed. I'm going to try not to make a mess of my picture, though, so I'm not going to. But I'm going to think about what happens if this were to be flipped up, right? Well, right now, the highest point on the graph is here at time 3. And at time 3, the velocity is 3, which means the speed is 3. That's the highest speed up here. But then when I look down here, right here, the velocity is -4, right? Look at that. Ooh, that's the lowest the graph ever gets, which means the speed is +4, which is actually greater than that one. It's like the extreme. What is the highest or lowest point? So they said when, so it looks like we're going to say time equals 7. And we looked at maxes and mins on the velocity graph. Those gave us candidates. Okay. Oh gosh, you can't even see that. So sorry. All right. So let's take a look at this last set of questions. In fact, the question is identical except for the time. So let's start with this. It says approximate the acceleration of the particle at 4 and then again at 6. So I want to find an approximation for the acceleration at 4 and at 6. Well, a big deal is like, well, how do we find acceleration? Remember, acceleration is the derivative of velocity, and derivative gives us slope. We're trying to find or estimate the slope on the velocity graph at time 4 and then again at time 6. Okay, let's start there. So here's my velocity graph. Here's time 4. If I lay down some spaghetti, I'm going to eyeball it here. Looks like I'm going down like a little bit more than 1 and over 1. So I don't know, I'm going to call it -1.5. It says approximate, so I have a little flexibility there, don't I? Let's do the same thing at 6. So here's time 6. Let's lay down a piece of spaghetti. Looks a little steeper than the first one. It's still negative. In fact, it looks like we're going down about 2 and over 1. So I'm going to say -2. As long as both of your answers are negative, and I think this one should be steeper than this one. It's not by much, but okay, that's all right. It's not going to change our next answers. So the question I have for both times, it says, is the particle speeding up or slowing down? So at first glance, we think, oh, well, she just asked for the acceleration. It's got to do something to do with that. I mean, I think in general, when we're driving a car, we think, oh, acceleration means we're speeding up. And so it would be, I think, a gut reaction to say, well, if the acceleration is negative, we're slowing down. Be very careful. Speed is the key word here, right? I'm going to even rephrase this. Speeding up or slowing down, I could really ask, is the speed increasing or decreasing? It's another way to write it or to say it. The reason I'm doing that is because remember, acceleration is the slope on the velocity, but then I start talking about speed. So we want to be very careful. I'm not saying that this is not an important number. It's just not going to tell the whole story. So I am going to go back to our graph, and this time I am going to make a mess. I am going to draw the speed. Actually, maybe I just draw the speed over here. Can I do that? So I'm taking this, I'm going to flip it up. This is already up there, that's 5. This goes up to what, 3? And then from 6 to 9, it came up to like a height of 4. Okay, sorry. All right. All right. This is the speed graph. I took my velocity graph and I just flipped it over. So that's my 1, 5, 9, and 10. I'm asking, is the speed increasing or decreasing at time 4? Well, here's time 4. Oh, look at that. The speed graph is decreasing. So at time 4, the particle is slowing down. The speed graph is decreasing. Versus at time 6, the speed graph is now increasing, which means at time 6, my particle is speeding up. So we're going to finish with that question, but we're going to pick up in our next lesson with this exact questioning and these exact numbers. But we're going to really talk about, how do these numbers play into this answer and what else do we need, okay? Because it's not really telling the whole story. So we'll stop there. But again, if we didn't have the speed graph or the velocity graph, like how would we have done that is really where we're going.